Hello, I want to tell you about the results of a recent research work in which we probe the quantum structure of space-time using a cosmic cataclysm. What we do is to check if the speed of light is a truly universal constant or if on the contrary it depends on the energy of the photons. For that, we measure the time that photons of different energy take to cover a certain fixed distance. If those times are different, it means that the speed of the photons is also different. Let me remind you that photons are described both as particles with a certain energy or waves with a certain wavelength. The lower the energy, the larger the associated wavelength, and vice versa. Why do we want to study this? Well, because for more than 100 years, our understanding of space-time and gravity has been described by the Albert Einstein's theory of general relativity. This does not include the quantum effects that were described for the first time by Max Planck and that we know must be important at very small distances, for example, very close to the center of a black hole. Therefore, we need a quantum theory of space-time and gravity. And the energy dependence of the speed of light that we want to measure in this study is precisely one of the few predicted possible manifestations of the quantum nature of space-time and gravity. At a distance of 10 to the minus 35 meters, which is called the Planck length, quantum effects should be important, which means that space-time cannot be considered a smooth continuum at that scale. It is then expected that the speed of a photon of wavelength comparable to the Planck length should be very much affected by quantum effects. However, the highest energy photon ever produced at the laboratory has a wavelength many billions times larger than the Planck length. Then, instead of trying to measure this effect in the laboratory, we do it using cosmic photon emitters. In particular, for this work, we use the so-called gamma ray bursts, or GRBs. These are cosmic explosions that release within a few seconds as much energy as the Sun in its entire lifetime, and are caused by the death of massive stars or when two neutron stars merge together. GRBs produce gamma rays, which are high-energy photons, but whose associated wavelength is still way too large compared to the Planck length. But because the gamma rays may travel for thousands of millions of years before we detect them, even a tiny difference in their speed could still translate in a measurable difference in time of flight. What we do in practice is to measure the emission of the GRB as a function of time for gamma rays of different energies, and study if we can establish a time shift in the observed patterns. That time shift is a known function of the gamma ray energy difference, the distance between the GRB and the Earth, and the characteristic length of the quantum effects of space-time that we call LC. In principle, we expect LC to be equal or similar to the Planck length, as I said before, but in this experiment is the free parameter that we try to measure. The GRBs are observed with the 70-meter magic telescopes at the Observatorio del Roque de los Muchachos in La Palma, which are sensitive to the most energetic gamma rays known to be emitted by GRBs. In the evening of January 14, 2019, we received the alert by gamma ray satellites that the GRB was happening, and 57 seconds later the magic telescopes were pointing in its direction. We measured 877 gamma rays in 20 minutes, which made this GRB the most intense gamma ray source ever observed, and it was also the first time that high-energy gamma rays were detected from a GRB. This GRB is at 4,500 million light-years distance, which means that the explosion happened when the Earth was still forming. This graph shows the measured emission as a function of time by different instruments. MAGIC was sensitive only to the first 20 minutes of emission, whereas in optical or X-ray, the emission was observed even 11 days after the burst. The result of this work is that we did not observe any time delay for high-energy gamma rays in the GRB emission. The first high-energy photon was observed 74 seconds after the burst started. Therefore, we can at least be sure that the time of flight difference between high and low-energy photon was 74 seconds at most. That would be the case if such photon was emitted exactly when the burst occurred and had accumulated 74 seconds of delay in its travel to Earth. Because we know the relation between difference of time and the characteristic length of quantum effects, we can translate the delta T limit into a limit to LC, which is actually close to the Planck length. In the future, we expect to be sensitive to shorter scales, even below the Planck length, by catching more distant DRBs with higher energy emission, and also by being faster in pointing at them with our telescopes, in such a way that we can catch the early emission, which is rich in time structure and will help looking for shifted emission patterns. Thank you very much for your attention.